A central dilemma sits in organizational life. We live in an increasingly uncertain world and simultaneously build organizations to create predictable outcomes where risk and uncertainty are often pushed to the margins of focus. In this show, we talk to one of the world's leading experts on the science of uncertainty and how it can help leaders embrace it more confidently. We explore the nature of uncertainty and how it affects systems and organizations. What we can learn from events such as the 2008 financial crisis. How methods being developed to understand the complexity of climate change could be of use to those running companies and even in our daily lives. It's not often that you get to talk to someone whose work won a Nobel Prize. So please tune in to an important, valuable, and exciting conversation.
Hi friends, welcome back to the Evolving Leader Podcast, the show born from the belief that we need deeper, better, and more committed leadership to confront the world's biggest challenges. I'm Scott Allender, co-host of the show, along with my friend and colleague, Mr. John Gomes. John, how are you feeling today?
I am feeling daunted and incredibly excited and curious. How are you feeling?
Curious, definitely. Open. Really eager to learn. I know we're going to learn a lot today. Feeling a bit like I am not smart enough to interview our guest today, but I'm going to give it a go. Because today we are joined by Professor Tim Palmer. Tim is a Royal Society research professor in climate physics and a senior fellow at the Oxford Martin Institute. In 2007, he was formally recognized as having contributed to the Intergovernmental Panel on Climate Change's Nobel Peace Prize. His life's work has been decoding the predictability and dynamics of weather and climate, including extreme events. He was involved in the first 5 IPCC assessment reports and was co-chair of the International Scientific Steering Group of the World Climate Research Program Project on Climate Variability and Predictability. For a large part of his career, Tim has developed ensemble methods, he'll need to explain this, for predicting uncertainty in weather and climate forecasts, and in 2020, Tim was elected to the U.S. National Academy of Sciences. And the theoretical side of his work explores questions around where climatic processes on different space and time scales interact. And on the practical side, he has developed and worked on the application of weather and climate forecast systems for malaria prediction, flood forecasting, crop yield estimation, and more. Tim, welcome to the Evolving Leader.
Thank you very much, and it's great to be here.
Tim, welcome to the show. How are you feeling today?
Well, listening to all that, I'm feeling a little nervous, to be perfectly honest. I'm pretty used to talking to my scientific colleagues, but now somehow talking to, the world's leaders makes me feel a little bit hesitant and reticent, but I'll try and do my best.
It's curious, isn't it? We're both sides of us are feeling somewhat anxious about
Nobody's comfortable.
That's good. That's a good place to be.
Yeah.
Maybe we shouldn't be. Okay.
Yeah. Well, let's get started with something here on uncertainty, because on this show we've explored how we can confront uncertainty in several ways, with the economist John Kay, with neuroscientists and psychologists and others. But in reading your book, it was both exciting and daunting, having little scientific knowledge of the topics you've devoted your life to. But it seems that in your career, there's been an almost intuitive approach to embracing uncertainty from the start. I don't know if that's a fair assessment, but can we start there?
I'm not sure exactly how intuitive it is, but throughout my scientific career, I've become very, if you like, conversant with what would be called nonlinear dynamics. And we could talk about what a nonlinear system is, but pretty much everything, we encounter in life is quite nonlinear. And when you think about uncertainty in the context of nonlinear systems, you realize that it's a kind of a challenging concept because, if the world was simple, we would be able to, things would be uncertain. It's not, things are always uncertain, but we'd be able to kind of put a bound on that uncertainty and say, pretty much every time we have to make a decision, we just add a kind of a fixed error bar or a fixed kind of uncertainty estimate, and that tells us, how uncertain things are going to be. But in a nonlinear system, it's just not like that at all. And it doesn't matter whether you're talking about weather or, the financial system or COVID or, the motion of asteroids in the solar system. Basically, what you find is that for a lot of the time, things are actually fairly certain and predictable, and your error bars are small. And then suddenly, kind of out of nowhere, the nonlinearities all conspire and the uncertainties become massive. And so the issue around uncertainty is not so much to just give a kind of an average estimate, but to be able to tell ahead of time whether you're in one of these pretty boring, predictable, nothing very interesting is going to happen types of situations, or whether something really dramatic and uncertain is going to happen, where the uncertainty is just going to absolutely explode. And that's the challenge. I don't know whether it's an intuitive idea or not, but it's certainly something that, an idea which has kind of, every time I study a new system, I just see the same thing manifest over and over again, that uncertainty tends to be sporadic. And real big uncertainty is sporadic and occurs on very specific situations. And the challenge for a scientist is to be able to determine ahead of time when we're heading for that special type of situation where the uncertainties explode.
And is it, in your opinion, true to say, because we've heard a lot of people saying this, but is it true to say that you think in certain respects our economic, political systems seem to be experiencing more periods of uncertainty and nonlinear kind of occurrences recently, or is that just, not true? What do you think?
Well, I don't know whether we're experiencing more of them, but we certainly experience them. And I think the financial crash of 2008 appears to be an example of an extremely kind of unstable situation, which in the book I tried to liken to a very famous weather event which occurred in 1987, which was famously misforecast by the BBC weather forecaster at the time, Michael Fish. Whether these things are becoming more frequent or not, I don't know. The real problem is that people tend to forget, that these things happen. And I tell you what kind of bothers me is attempts to remove legislation which was designed originally to try to damp those types of instabilities. We remove them at our peril, because then we open the system back up to these things happening again. And that bothers me a little bit about the way, in which some of the financial regulations seem to be going in recent years. But maybe that's too political a statement. I don't know.
Well, I think it's the cycles that you're seeing there in terms of political memory around the legislation that was instituted into the banks and financial systems is being unwound, isn't it?
Yes. Of course, it's wrong to talk about cycles as if this is something very periodic and that, we can predict exactly when it'll happen because we know the time, when it last happened. These things aren't periodic. They're aperiodic. And so predicting these instabilities and predicting when these uncertainties will become massive is not really an exercise in statistics. It's an exercise in understanding and modeling the underlying dynamics. That's the crucial point.
So let's dig into this then and imagine that we don't have to imagine. It's true. We don't understand any of this at all. But can we talk about some of the most kind of fundamental scientific concepts of uncertainty that you explore in the book, and pick the ones that you think are best, because you talk about things like the geometry of chaos, and it's intriguing. But how can we understand those in a way that allows us to perhaps apply some of that thinking to the challenges we might be facing in running organizations?
Okay, well, there's two different questions there. I mean, let me just answer one question, which we could return to, if you like, in the future, which is, when we talk about uncertainty, I mean, what is the source of that uncertainty? And there's something quite kind of fundamental here, which distinguishes two types of systems, at least as is conventionally thought in the world of physics. Because when we talk about chaotic systems, the weather being an example, many examples in biology and in engineering and all sorts of things are chaotic. And now we say those, though, we talk about the butterfly effect, the fact that, we don't know every last detail about, for example, the initial conditions for one of these systems makes it difficult to predict the future. And what we're saying at a kind of philosophical level is the uncertainty arises because we humans don't know everything that can be known about that system. And the fact that we don't know even very small details can make the system unpredictable to us. Mm-hmm. But if you were to talk to somebody that looks at atoms and elementary particles and the things that are governed by what's called quantum mechanics, they might say something rather different. In fact, they're very likely to say something very different, which is that it's actually the equations themselves, the fundamental laws of physics, which are uncertain. It's nothing to do with whether we humans are uncertain about them. Now, this is something Einstein hated. He famously coined the phrase, God does not play dice. And it was a way of saying the laws of physics can't be inherently indeterministic, doesn't make any sense. But at least at face value, the Nobel Prizes for physics that were awarded this year kind of lend support to the idea that actually the laws of physics aren't determinate in this way. So there are these two fundamental differences if one's going back to basic science. A philosopher would call the first epistemological, means the uncertainty is the fact that we don't know everything about the system. And the second is sometimes called ontological. It's kind of the notion of reality is uncertain. And that's a really interesting, I think, debate. It may not be of interest to kind of leaders of FTSE companies. Perhaps in their spare time it might be. But it's a really kind of serious and important issue in fundamental physics.
Well, I wonder whether that's a relevant question. So it feels like it is, because if you take the approach that we just need to know everything,
right,
and all the finite detail to be able to eliminate uncertainty.
Yes.
But you're saying that there is an underlying uncertain level at the quantum mechanics.
Well, that's right. But of course, the point is, with a system, you can't know every little detail. You can't measure every gust of air it goes around every little hill and mountain in the world. So you have to recognize that, there are uncertainties. And similarly, you don't know everything about the global economic system. You may know some kind of macro details, but you don't know every detail.
But do you get approaching more knowledge? So if the world was in the future and there was unlimited computing power and we have the singularity and we have an abundance of sensors and all this kind of, just as a thought experiment, do we move closer to that, or are we chasing something that becomes elusive? I don't know.
We actually, that's a good and interesting question, which was one of the chapters of my book, which is actually one of the, at the turn of the millennium, the world's top mathematicians framed a set of about 10 unsolved mathematical problems that needed solution. And actually one of them was exactly that, applied to the equations of fluids. In other words, if we could measure, for example, if you could measure every little drop of water that flows over Niagara Falls to the precise, as accurately as you liked, would you be able to predict the motion of the water as it flows over Niagara Falls, by the time it got to the bottom, let's say? And believe it or not, that is an incredibly subtle and difficult problem that And the answer is we don't know, actually. The mathematics is kind of too difficult, actually, to give a definite answer to that question. So we really don't know. So it's a kind of a really interesting question, actually. If you had an equation which had no random terms in it, the fluid dynamical equations have got no random terms in it. Everything looks very precisely determined and so on. And yet we don't know if we knew absolutely every tiniest drop of water to arbitrary accuracy. And as you say, we had an infinitely big computer, whether we could work out what would happen in the future without uncertainty. We don't know the answer to that question. But the evidence suggests we won't, that there actually are things that conspire against knowing that. Now, I think the big, if I had to put out one kind of key message here, is that uncertainty it's two things. It's kind of really it's an interesting topic, but it's kind of intrinsic. I mean, your question perhaps touches on this. It's kind of intrinsic to the system that you're studying. And if you claim to, or if you aspire to understand that system, you've got to be able to understand the inherent uncertainty that is associated with, predictions that you make with that system. And I think the bottom line here is that, if you're the sort of person that might lazily say, oh, well, we'll make the study that we want to do, and we'll kind of do a bit of a risk analysis at the end of it all, just so that, it keeps people happy that we've thought about potential kind of, things that might not go quite according to plan. If you treat uncertainty as an afterthought, you're likely going to run into trouble, and that's the kind of the message. And so a lot of my career has been persuading my colleagues, particularly in weather and climate, and I'm trying to do this now, in the economics area to some extent as well, to treat uncertainty with as much kind of emphasis and importance and so on as the actual things you're trying to predict. So whether it's rainfall or, temperature or GDP or inflation, to actually treat predicting the uncertainty in those quantities with the same level of kind of commitment and resource and everything else as to the quantities themselves. And there are two things about it. I mean, one is that you will then hopefully not get caught out by these periods which were explosively uncertain, where you had completely failed to predict that. And so you advise people really badly, like Michael Fish said in 1987, oh, don't worry, there'll be no hurricane, meaning you can go out, as per normal, you don't have to change any plans. And of course that was people lost their lives in that storm. So that was a very bad thing to say. And sort of secondly, it's telling you when you correctly estimate the uncertainty in your predictions and reality always lies within the error bars and so on. I mean, it's telling you you're actually understanding something about the system and that you therefore can have much more confidence that what you're doing is going down the right track.
So I was trying to get my head around Heisenberg's uncertainty principle, which I think I've done. But for John's benefit, I'm wondering if you can help us try to understand the definition of this principle.
Well, if you look it up, it sort of says that you can take two variables in quantum mechanics, like the position of a particle and its speed, let's say, sometimes framed in terms of momentum, but it's the same as speed. Heisenberg's uncertainty principle says, the more you know about one of those variables, so the more accurately, for example, you try to to measure the position of a particle, the more uncertain you are about its speed. Now, the interesting question to me is this question of what actually is the origin of the uncertainty in Heisenberg's uncertainty principle, and that's where it comes to this kind of ontological versus epistemological question. In other words, is it, it's interesting. Heisenberg himself originally thought that it was epistemological. In other words, the fact that there was uncertainty in the speed of the particle was just because we humans couldn't measure it properly. Or if we tried to measure the position, it kind of messed up our measurements of velocity. But Niels Bohr, who was, a colleague and perhaps slightly the mentor of Heisenberg, kind of reprimanded him about this. Says, no, it's nothing to do with us humans. It's to do with the intrinsic equations of quantum mechanics that gives rise to this. And that's what I say. Einstein hated this. And in my view, this is actually still an open question. And in my book, I try to say, whilst on the one hand, the consensus view is that Heisenberg's uncertainty principle is telling us ultimately about the fact that the laws of physics are inherently indeterministic. They're not deterministic. There is a kind of a minority view, and I'm in the minority, I have to say, so I can't kind of push this too strongly because it's not yet clear, but I'm of the view that actually Einstein was right about this, and one can frame things in a way where quantum mechanics, quantum uncertainty is actually seen as a result of our human, the experimenter's uncertainty. But, we're talking about topics which are not settled and are uncertain themselves. So it's an interesting kind of time and place to be doing fundamental physics in many ways.
Yeah.
Often the kind of the narrative around 2008, the financial crisis, was around it being a moral failure of banks and regulators, and that there were inappropriate systems and checks and balances in place, all of which are probably true. But what if you went back in time and you had the opportunity to kind of use what you know and what has been learned about uncertainty and could institute that somehow?
Well, okay, yeah. I mean, this is something which I talk about a bit in my book. Let me just wind back a bit, because what I did in my own field of weather forecasting is to if you go back to the I mentioned Michael Fish, so we're talking about the 1980s, if you like. In those days, it was almost considered, to be kind of letting down your profession if you were a TV or media forecaster to kind of admit there was any uncertainty. So in those days, it will be sunny tomorrow, it will be rainy the next day, it will be windy the day after that. Everything was definite and everything. And I tried to argue to my colleagues that it wasn't like that. And we developed this idea called ensemble forecasting, where you literally run your weather forecast model. Instead of running it once, you run it, say, 50 times with very, very, very slightly different initial conditions, which reflect the uncertainty in the initial conditions. The fact that, the observations of the weather are never completely perfect, and they certainly are kind of sparse in some parts of the world. And we also added noise to the model equations, because the equations, how you represent the equations on a computer, actually introduces uncertainty as well. So we did that, and we showed that you could get credible, then we showed that what would happen is that for a lot of the time, the forecast would actually look pretty similar for 5 or 7 days or so, and then they would start to diverge from each other. But from time to time, we found that the forecast would actually diverge almost from the beginning. Now, people sort of said, well, I don't think that happens. That's a bit of a weird situation. And then the famous October 87 storm came along, and we were able to show retrospectively that that actually was an example of an explosively unstable event. So literally, flaps of butterflies' wings did make a difference between whether it was going to be a hurricane or just a kind of nothing type of weather event. And it was that storm actually which sort of turned the tide. And eventually, the colleagues agreed that this was a good way to spend computer time to run the forecast 50 times. And, and you can thank this for, or not thank as you like, the fact that these days on your weather app, you will see probabilities of rainfall. You won't see definite rainfall amounts, probabilities of rainfall. It gives you an estimate of uncertainty. But what is more important, I just say this in passing, what is more important, much more important than a weather app, is the fact that nowadays humanitarian organizations and disaster relief organizations can make use of these ensemble forecasts to determine when they can go into a region that is at threat of an extreme weather event and hand out, medicine and shelter and water and even money, actually, financing, ahead of the event, anticipating the event. And, in the old days, the deterministic, the single weather forecast was so unreliable that they couldn't do that. If they did that every time there was a kind of a potential storm coming, they would just run out of money because they'd have so many false alarms that, they'd be wasting their money most of the time. But now what they do is they do a kind of a cost-benefit analysis, and they say, okay, we've worked out, based on, as I say, cost-benefit, cost-loss analysis, that when the probability of an extreme weather event exceeds, let's say, 70%, whatever it is, some threshold, then we know it's worth going in, the benefit of going in and saving lives and so on will be worth it. We're prepared to take the hit that 20% of the time that event doesn't happen, knowing that 80% of the time it will happen. So having a probability, the probabilities are based on these ensembles. So if you have a probability of 80%, it means 80% of the ensemble forecasts are showing this extreme weather event. Then it gives them an objective criterion, for taking anticipatory action. And that's completely transformed the way, as I say, humanitarian agencies work. In the old days, they would just wait for the event to happen, if it did happen, and then go in. And of course, it used to take a week or something to get the medicines distributed to areas that were stricken by, a cyclone or a hurricane or something. So that's for me has been a real kind of justification for this. Okay, now in writing the book, I tried to sort of argue, well, could this technique be applied in other fields? And it turned out, actually, I wrote the book during all the COVID lockdowns, and it turned out actually that the epidemiological models that were predicting, the effects of COVID in terms of hospitalization and deaths and so on, I mean, people realized that individual models were massively uncertain, and that they used they took inspiration from what had happened in meteorology to develop these ensemble prediction COVID models. And I was kind of quite heartened as the COVID thing kind of evolved to see how much, collaboration there was from, for example, in the US, all the groups around the US pooled all their data into a central database of kind of on COVID ensemble predictions, and something similar happened in Europe, and so you got these kind of probability distributions, so that you could estimate not only the most likely numbers of deaths and hospitalizations, but perhaps more importantly for policy, the sort of plausible worst case scenarios, because that's sort of what you want to avoid. And then I started looking at economics with this question, actually, of 2008 in mind. Was the 2008 crash an example of the kind of Michael Fish storm, of an exceptionally unpredictable event or not? The problem is that the kind of traditional kind of macroeconomic models based on what they call neoclassical kind of equilibrium theory, they just weren't suited. You couldn't even ask that question sensibly in such a model. But I started discussing with some of my colleagues in Oxford this kind of slightly more modern type of what are called agent-based models of the economy, which try to kind of model the economy at a micro level with these agents, which could be banks or businesses or hedge funds or whatever, individuals even, and managed to eventually find some people that had started to do ensemble forecasts for with these agent-based models of the economy, and found one person in particular who had started to study the 2008 crash. And the evidence from these ensemble models was indeed this was like the fish storm, in the sense that so if you had an ensemble of agent-based models, you would not have predicted deterministically that there would be a crash, but you would know that this was a period of enhanced instability where, the likelihood of a crash, just the same with the Michael Fish storm. The 2 days before the Michael Fish storm, even today, if that Michael Fish storm was to happen, the exact same one, we wouldn't know for certain that there was going to be a storm 2 or 3 days before. But now we would have a very clear estimate of probability. Turns out it was around 30-40% 2 days before the storm. And that would be similar today if that same storm was to happen. And in a similar way with these ensembles of agent-based models, it looked like, a similar type of probability if we're, going, say, I don't know, I can't remember now, 6 or 9 months before the crash, of the crash occurring. Now, these ensembles, they are expensive. You have to run your model many, many times. It's not cheap, but I would claim the information you get is worth it, because it makes for a much more reliable system than, when you're making a forecast without any estimate of uncertainty. I mean, I kind of liken it to going to an astrologer. If you went to an astrologer and asked them for an error bar on their prediction that you'll meet a tall, dark stranger, you'll just get a blank look. And it's kind of telling you that that's not scientific. And in a way, my own view is that meteorology as it used to be in the 1980s and before, in that sense would fail the economic test. And I think, to be honest, a lot of economics models similarly fail the test because they haven't really thought through properly how to represent and estimate uncertainty. But I think, there are encouraging signs, I think, in terms of what I found in the chapter I wrote. But I say this not as somebody who's an expert in economics. I've just come to it from a particular angle in my own work, and I think there's a great promise, providing people take it seriously enough. You can't do, as I say, just repeat, you can't just do this as an afterthought. Oh yeah, we've made our prediction, we'll just stick an error bar on. It doesn't work like that. That's going to fail. You have to incorporate the uncertainty estimates in your intrinsic methodology kind of from the start.
How widespread has the adoption of ensemble methods been? Can you give us some sort of sense?
Well, in my own field, it's now absolutely universal. It's completely universal. There's no question whatsoever. People recognize it. That's been great for me, and it's illustrated, by the way, a principle which I think goes back to Max Planck, who was the famous founding father of quantum mechanics, who says that you never convince your colleagues about something. It's just that a new generation comes along, the old ones die off, and a new generation comes along kind of not knowing any different. And I kind of feel that's happened a little bit with the ensemble stuff. I mean, I had some colleagues who I like very much. I admire them, and I enjoyed, debating with them. But some of them wouldn't, their views would never change. But the young guys come along, guys and girls, in general terms, and, they say, well, this is a no-brainer. This is such an obvious thing to do. And so that's kind of the way it is. And every Met Center in the world, the IPCC, everything, that's to do with weather and climate prediction is now based completely around ensembles. It's a done deal.
Hi, this is Emma Sinclair, business psychologist, occasional co-host, and fan of the Evolving Leader podcast. Did you know that we also have an Evolving Leader YouTube channel where we upload snippets from many of the podcast episodes? It's a visual feast of leadership goodness. Just go to YouTube, search for the Evolving Leader, subscribe, like, and comment. Now, back to the conversation.
Can we talk about the ensemble method specifically around climate change? Can we hone in on that a little bit? Because I'd love to understand the milestones of how your work has gotten us to our current understanding of the world's greatest challenge.
Well, I think one thing I'd like to say about climate change is because I realize, of course, unlike weather forecasting, climate change has a kind of a political angle to it, which somewhat divides society still, I guess. But in the book, I've tried very hard to separate the science from the politics. And I've got 2 chapters about climate change. One is very much a science chapter, and one is much more of a, if you like, politics type of chapter. But just to sort of to try to explain my position, just go back to weather forecasting. If I said to you next week, there's a probability of 80%, or let's say in 4 days' time, there's an 80% probability it will rain in London or somewhere, wherever you want. And then I say, well, okay, do you believe it's going to rain, or do you believe it's not going to rain? And probably you just shrug your shoulders and you would say, well, I neither believe it nor I don't believe it. I just, I accept what you tell me. There's an 80% probability. So then the question is, well, what are you going to do with that knowledge that there's an 80% probability of rain? Well, you might say, okay, well, if 80% sounds a large enough number, that I'm going to take my umbrella to work. Or 80% is a large enough number that the the outdoor picnic that I was planning to have, maybe I'll have it a day earlier or something like that. So in other words, you make decisions. You don't have to believe anything. You just make use of that information to make decisions. And my view is it should be exactly the same with climate change. We have models which are based on the laws of physics. They're the best, given our resources, they're the best we can do. We recognize that the models are uncertain. We've tried very hard to represent the uncertainty in the models as best we can. We have a range of different models around the world, where uncertain assumptions are made differently according to which group. So we have this kind of ensemble of models. We run different scenarios for carbon emissions with all of these models. This is what sort of the IPCC does. And you end up with these probabilities. So for example, I went through a scenario where the world warms by, what would happen if the world warms by 4 degrees Celsius? And you don't have to think very hard about it to realize it would be a pretty catastrophic world. There would be heat waves in large parts of the subtropics in particular, where the human body actually couldn't withstand the temperatures anymore. So you'd either die, or you'd spend your whole life or you'd spend weeks at a time in air-conditioned buildings, or more likely you would migrate somewhere polewards. But then, we've got all the problems with sea level rise and it's just a ghastly scenario. So, okay, you say, well, what's the probability of a 4 degree warmer world based on let's say based on an assumption that we're not successful in cutting back our carbon emissions politically. And then you come up with an answer of, let's say it's around 50%, something like that, 40, 50%. Don't know the exact number off the top of my head, but something of that ballpark. So then the question is, if you are, should if we cutting carbon emissions clearly does cost money. I mean, weaning ourselves off fossil fuels is not straightforward. Is it worth it in terms of the two things, in terms of the economic and indeed social and humanitarian impacts that will do to people of a 4-degree warmer world, times the probability of that warmer world occurring. And I try, in one of the chapters of the book, I try to kind of go through how you might make that judgment about whether it's worth it or not. And in a sense, I don't want to, I'm not a member of an environmental organization, so I'm not going to kind of try and preach to anyone about what the answer is. What I'm saying is that question about whether it's worth it in terms of the impacts of climate change times the probability or the likelihood of it occurring. I mean, that involves value judgments. And, I'm not as a scientist, I'm not particularly, expert to make those judgments. I know what I think, but, people have to make their own minds up. But the point is, at no stage do you have to say, I believe or I don't believe in climate change. It's just not a logical question to ask. And I think it would be really helpful in some of these kind of debates if one could take that whole kind of word out of the debate and just say, A, what does the science say? And the science is uncertain. There's no question about that. The science does not tell you it will be 4 degrees warmer or 6 degrees warmer or 2 degrees warmer. It tells you about probabilities of different occurrences. Some would be, small perturbations to the climate. Others would be quite catastrophic. And the question, as I say, then, there's a second question is, based on value judgments, is it worth taking action based on the likelihood of really catastrophic changes? So, when Greta Thunberg says, listen to the scientists, I mean, the scientists can only say so much. The scientists can't tell you, and they shouldn't tell you really, whether, therefore, you should take action. They can tell you that if we don't if we continue emitting carbon dioxide into the atmosphere, the risk of these extreme weather events will get larger and larger. That is a scientific fact. But whether we should, therefore, cut our emissions, that involves value judgments. And in the book, I try to very much, separate those two things out by putting them in two separate chapters.
I think it's an incredibly useful way of thinking about things because it level sets people to have a different kind of conversation about the value judgments, the moral reasoning component of that, which is where they often start. And then it's one set of value judgments against another rather than and kind of weaponizing the data for motivated reasoning. So I think it's a really helpful way of thinking about things.
So I'm curious, how do you see the science of uncertainty developing over the next decade? What are you imagining will be the next series of developments and applications?
I think one of the really big questions in our field is going to be the role of AI, and in my own field of meteorology, there's an enormous climate. There's enormous debate about AI, and I think this is an area where one, on the one hand, has to be aware of the power of AI, but also the potential pitfalls of AI. And I think when it comes to uncertainty, there are pitfalls because, what AI is very good at doing is kind of interpolating between, points in a data set. You give it a training data, of dogs and cats and things, and you give it a picture of a cat that perhaps it hasn't seen before, but it kind of interpolates between all the cats that it has seen. And so it kind of knows it's a cat. And similarly, a dog, that interpolates between the dogs, it knows it's a dog. The problem with problem with AI in general is that it's not necessarily good at extrapolating, of finding, of being confident about something that lies way outside the training data. And this is a problem with climate change. People talk about, we can use, I'm a great believer in using the laws of physics to make predictions about climate change. But, that is expensive. It's computationally expensive. And some people say, we can, we just do it with AI. The problem is that we're talking about predicting weather events that just have never occurred in the past. And they've certainly never occurred in the time frame where the training data, on which the AI is based has seen. So, and that's where things become dangerous. It does bother me. I'm not answering your question exactly, but I think one thing that bothers me is of an overconfident. If you develop a system based purely on AI, it may be overconfident because it will just because it's never seen extreme events which can happen. It will just discount them as very unlikely and so on. So looking into the future, AI is a great tool, but we have to be very, very careful in how we use it and use it kind of judiciously, combining it with the laws of physics. So that's one area. In my own field, there's another, whole area around quantum computing, whether that's going to be a big area, and because quantum mechanics is uncertain, maybe you could say, well, okay, maybe that's good, but again, there are pitfalls with quantum computing as well. So I'm I don't know, I can't answer your question terribly well, but I think it's really important not to get sort of sucked in by hype, and just to make sure you really understand a new technique that's being proposed, that you really understand what it's doing and you understand its potential shortcomings, because you could end up having invested a lot of time in representing uncertainty to suddenly find your new technique is massively overconfident and incapable of seeing the real uncertainties that occur. And I think we've kind of seen that a little bit with some of recent AI applications.
Where do you see uncertainty sitting into the kind of educational curriculum? Because it feels that it hasn't kind of gone down into secondary education, or even sort of across other fields. What's your thoughts about how it needs to progress there?
I haven't given this a massive amount of thought, but now you kind of mention it, it does indeed sound like a topic that really needs better understanding. I remember as a schoolboy learning Newton's laws of motion, and the fact that if you projected a cricket ball or something at a certain angle with a certain initial velocity, then you could estimate precisely where it will land in the future. And of course, those types of problems are the exception rather than the rule. And one of the great things I think actually about chaos theory is that there are very, very simple models which now can be used and pretty much understood at sort of GCSE level, which not only illustrates this concept of inherent uncertainty, but this idea that sometimes systems can be very predictable, and then just very occasionally they become extremely unpredictable. I think if I had to teach one thing to a well, it wouldn't necessarily even have to be scientific. This is a sort of general point that, I would try to explain what a nonlinear system is. I think that can be done reasonably easily. And to say, when you have nonlinear systems, these can look as if they are predictable for long periods of time, but then suddenly become very unpredictable. In my book, by the way, I cite the example of planets going around the sun. We kind of think of planets going around the sun as something that's completely clockwise, clockwork and completely predictable. The length of the day, when the tides will occur, the fact the sun sets in the west, rises in the east. We think of these as absolutely immutable and unpredictable. But I show an example of a kind of a type of solar system that looks like it's predictable like that, and it is for very, very long periods of time. But then suddenly, all the planets just suddenly explode away from each other and get sucked off to infinity. And that's an example of one of these very intermittent instabilities, which, as I say, I think, that we see it with the economy and with weather and all sorts of things. So just teaching that as a basic concept with some very simple illustrations is something that wouldn't be too hard to do. It kind of almost is general education. It doesn't even have to be done in it's not like we're talking specifically about physics here. We're just talking about life, kind of life in general. So
that's fascinating. Can you, as we run to the end of our time, can you bring to life what, maybe there isn't one, but what a typical day looks like for you? What does your work look like, or your week look like?
I'm in a sort of unusual. I work at Oxford University, but I have a rather unusual position at Oxford, in that I'm not like a regular don, if you like, but what's called a Royal Society research professor. So, the regular day for most of my colleagues would actually be doing a lot of teaching to undergraduates and then tutoring them in their own particular colleges and so on. And I have a position where I'm just funded to do research. So I have a group of PhD students and postdocs, and we work on these issues to do mainly around weather and climate, but I have some side interests, for example, in quantum computing and in areas to do with actually the foundations of quantum mechanics. So I have a kind of quite a broad, and I have interests in the brain. We didn't talk about that much, but that's another area in my book, how, what makes us creative people that we are. And I think noise, the role of noise in the brain is important here. Anyway, so most of my work is, so what would I do? I'd spend maybe half of my day talking to the PhD students and postdocs, and really the rest of the time, I go to conferences and things, but I really do try to have as much time as I can just thinking about stuff. And I always remember a comment by somebody, it was like, I think it was Richard Feynman or Murray Gell-Mann, one of these really famous physicists, where he was being interviewed like I am now. And the interviewer said, well, what's the secret of your success, let's say Professor Feynman? And he said, I don't know what the secret of success is, but I can tell you what the secret of failure is. So, that's interesting. What's the secret of failure? He said, the secret of failure is a full appointments diary. In other words, you won't go anywhere in science if you fill your whole day up with meetings and and interviews, maybe. Yeah. You know what I mean? So so a lot of my day actually isn't particularly, if you looked at the diary, you just see a big blank. But actually, it's time I really do value in just thinking. Actually, and I don't think we do enough of that. It's just horrendous how much now people's lives are just wall to wall with meetings. These are really bad.
Well, I think that observation is absolutely resonant and true for every leader. If you don't have time to think, when I started work, my boss said to me, you need to be a thinking leader. You need to set aside time to think, and that's become just increasingly a luxury for many people. So, well,
you have to put your foot down somehow and just say that I'm sorry, but it's not going to work unless I do that.
Professor Tim Palmer, it's been an absolute pleasure. You've made what is one of the world's most challenging topics and important problems to solve very accessible and enjoyable to talk about. So, very appreciative of your time. Thank you.
Thank you very much. It's been great. Thank you.
And until next time, remember, the world is evolving. Are you?